Hello everyone. Thanks to attend my presentation. My today's presentation topic is optimal leak vector selection for the output constraint leaky filter input least mean square algorithm. My name is Dongyuan, coming from Nanyang Technological University in Singapore. In today's presentation, I will firstly introduce current problem of the active noisy control technique. Then I will report our proposed method to solve this problem. Finally, I will show the simulation result of this new method and conclude the whole slide. So what's the active noise control? Active noise control is a technique which uses the secondary source generating an anti-noise to suppress the primary disturbance and the specific location. It's usually regarded as an efficient solution to deal with low-frequency noise. However, its performance is also hampered by some hardware imperfection, such as output saturation. What's output saturation? When the hardware has insufficient output power to attend the disturbance, saturation distortion from the overdriving amplifier and actuator will deteriorate both attenuation performance and residual sound quality. It may result in the divergence of the adaptive algorithm in severe cases. To solve this problem, there are many existing algorithms. The first algorithm is nonlinear FXMS algorithm, which requires an accurate estimate of the saturation amplifier model. However, in practice, this kind of model is hard to get. Another type of algorithm is to truncate the output signal to restrain the output power, such as clipping rescaling 2GD FXMS algorithm. However, this method will bring some amplitude distortion to the output signal. The third one is the leaky FXMS algorithm, which can reduce the amplitude distortion in the output signal. However, its critical parameter, leak factor, usually is determined by trial and error. In this presentation, we will propose a method to select the optimal leak factor for the leaky FXMS algorithm. In that slide, the figure 1 shows the block diagram of an ANC system with the saturation effect. In this picture, the P stands for the primary pass, the WN stands for the control filter, and S denotes the secondary pass. To simulate the saturation effect of the system, we insert a nonlinear saturation function F in between the control filter and the secondary pass. This saturation function can be a sigmoid or arrow signal. To reduce the saturation distortion, the leaky FXMS algorithm is applied to update the control filter. As shown in equation 1, in this equation, the mu stands for the step size of the algorithm, and the gamma denotes the leak factor, which decides how tight the algorithm constrains the control filter. Then the output of the system input to the saturation function, the disturbance minus this result to get the error signal. These two algorithms describe the whole progress of the leaky FXML algorithm. To select the optimal leak factor, we first define an active noise control cost function with a specified output constraint given by the equation 3. In this equation, the top term is used to minimize the mean square error of the system, and the bottom term is used to confine the output power, where the rho square denotes the maximum average output power or the rated power of actuator, which can be measured by the experiment or get from its data sheet. To solve this problem, we bring in a slack variable theta square, which is given by the equation 4. Based on this slack variable, we can list out the Lagrange function of the equation 3, which is shown in the equation 5. In this equation, the lambda is Lagrange factor. By solving this Lagrange function, we can derive the optimal control filter as shown in equation 6, where the Rx and Rx prime reference the autocorrelation matrix of reference signal and the filtered reference signal. The P dx prime denotes the cross-correlation vector of filter reference signal and disturbance. The optimal Lagrange factor lambda O is obtained at the equation 7. In this equation, from this equation, we can find this optimal Lagrange factor is related to output constraint. Since the anti-noise is linear correlated to the disturbance, so their correlation coefficient approximate 1. So we can get the equation 8. Bring this equation back to equation 7. We can derive the optimal Lagrange factor as shown in equation 9. In this equation, we can know the left of this solution is the ratio of real system output power over the rented power, and the right of this solution will be defined as the system nonlinearity degree in the following page. To simplify this analysis, we assume the input signal xn is a zero mean white noise. So the optimal control filter with output constraint can be rewritten as equation 10. In this equation, the theta x square denotes the input power. We also can derive the optimal solution of the leaky FXMX algorithm as equation 11. In this equation, the I denotes identity matrix. So next equation 11 equal equation 10. We can derive the optimal leak factor gamma O as shown in equation 12, which is the relative input power and the system nonlinearity degree. To test the performance of this optimal leak factor, we also carry out 3 different simulations. In first simulation, the primary path is the sine tone at the power constraint of the system is 0.775 square over 2. The secondary path is set to 1 and 0. The step size of algorithm is 0.005. The figure 2 shows the convergence path of the leaky FXMS algorithm with the optimal leak factor for different primary paths. In the figure, the red dashed line refers to the output constraint, and the black dot denotes the optimal solution with constraint, and the red star stands for the optimal solution without constraint. When this optimal solution without constraint, no case inside the output constraint or at the output constraint, we can find this optimal leaky FXM algorithm can reach this optimal solution. So if the optimal solution outside of the constraint, then the optimal leaky FXMS will reach another solution, which is optimal control filter under the output constraint. In the secondary simulation, we set the secondary path at another path, and the step size is 0.001, and the primary noise is the white Gaussian noise. Then the figure 3 shows the result of this simulation. From this figure, we can know the second simulation result is similar to the previous one, which indicates the optimal leak factor can help the leaky FX algorithm to achieve the optimal solution under the output constraint. In the final simulation, we use the real measured primary noise and the secondary source from an air duct. Then The output constraint is 0.75, and the primary noise is the sine tone, and the major noise is the Gaussian noise. So the figure 4 shows the spectrum of the error signal and the control signal of different algorithms. From figure A, the figure A shows the disturbance at the error microphone without control. From this figure, we can know the power of the disturbance is 18.5 dB. When the system uses the FXMS algorithm, we can see the disturbance reduced to the 61.1 dB. However, there are many higher harmonics in the error microphone. The control signal of the FXMS also violates the constraint. Finally, if the system use the proposed leaky FXMS, we can see the disturbance reduced to 73.4 dB, but there is no any distortion in the error signal. Well, this algorithm also confines the output signal of control filter within the constraint. From this simulation, we can know the proposed optimum leaky factor can successfully ascertain leaky FXMS to confine its output signal within the constraint. So in this paper, an optimal leak factor is proposed for the leaky FXMS algorithm, which assesses ANC system to achieve the best noise reduction while restricting the average output power within a specified range to prevent saturation distortion. Furthermore, compared to the previous related work, this optimum leak factor does not require any certain saturation model and the impulse response of the primary path, so it can be easily calculated in practice. That's all. Thank you for your listening.